Oh, actually, in our previous lecture, which was extended 1 hour and a half, but we seems fully understand how this equation appear almost in all of the Baltic approximation, that it's result in now your Stokes equation and equation for the entropy, and this are in fact 8 equations satisfy to 8 boundary conditions. So actually we formulate everything. So now we can discuss, and there is special separated paragraph about accuracy verification by nonlinear scaling actually. We will proceed with nonlinear scaling, and after this nonlinear scaling we obtain the characteristic value of all the parameters, and we will see that the initial assumption which is shown on this picture, that initial assumption on which all this system was derived is satisfied. So this is our goal. To reach it first, let's remove. You just write down the name of the chapter, 4.2. 4.2. Accuracy. It's the name of the chapter. Accuracy verification by nonlinear scaling. And actually we will do very simple things. I'm removing this equation, but of course we will refer to this equation somehow. Nevertheless, they are kept in U, so I will be referenced on this equation of this equation system when proceed further to this estimation. And quite natural estimation to understand the typical value of the problem is just to involve some nonlinear term, because from linear term it's quite difficult to make estimation, because linear term could be balanced only at one level. So you just balance one value with another value, so you can balance only values that exactly equal to each other. But in nonlinear situation, it's much more better case, because we can involve imbalanced nonlinear term, and this nonlinear term will give us the various results which are directly related to the preferable balances and so on. So actually this situation is necessary to use solving any problem, because actually if you state the problem in the way that it's difficult to reach the proper solution, it's not the case. It's better to avoid this situation. So let me state the system the system which was just removed, this complete system with all the boundary condition and everything, is formally similar to the well-known system obtained in Busse approximation. For example, you can see work of Glatzmeyer, Roberts, Christensen, and Aubert, and many others, including myself. The similarity is especially clear in the superadiabatic entropy. For the superadiabatic entropy, which is written here, but let us repeat it in number. So superadiabatic entropy, we will denote superadiabatic entropy by just small s. Then the s itself is s, and so that it is derivation from superadiabatic entropy means like that there is adiabatic entropy, and we consider some general entropy. And so eventually the deviation, this from this is quite small, but it could be dependent on coordinate and time as well. While maybe if you remember from my previous lecture, this adiabatic entropy depends only on time, not in space, but only on time. So and eventually we can get this expression, which is just repetition of what I showed in the previous lecture. There is expansion coefficient, there is the adiabatic density, then we have pressure, not the pressure itself, but normalized pressure which is on top of the adiabatic pressure. So it's just near the adiabatic pressure term, which is actually the difference. And this only this play a role. And then there is a contribution from the temperature variation. Temperature variation is this contribution from the temperature variation could be represented like that. We divide Cp by Ta, and we have such a value which we regard like a temperature variation. We use slightly another, not slightly, but other values than we used. Frankly speaking, in our previous lecture, we didn't use any notation for this variation of the temperature. We just say that there is this variation is small and put it everywhere. But here, because we want to estimate some sort of the real values, so we just made the special notation for the variation from the temperature. So actually, this superadiabatic entropy from actually it's coming from formula 4.22 and it will be considered more below, and is substitute to the formula 4.48 and 4.78 formula, which we just put the most recent formula. One formula is about the entropy equation, and another from the okay, so and actually in this formula we already neglect the superadiabatic pressure, which is again just I remind you that just to remind you that this theta in our case is equal T minus TA, and the pressure, this pressure, small pressure, is in our case P is equal capital big pressure minus adiabatic pressure. It's just to remind you. And let's number this formula. This is just repetition. Here we can put the dot, and this is the number of formula 4.8 A. Okay. So actually, to get this relation one, we neglect, as already told, this superadiabatic pressure contribution compared to superadiabatic temperature, and the system obtained after such a substitution is practically equivalent to the Busse system. I already showed you this Busse system, and I will not repeat it again. And a small deviation from the complete equivalent is only in the boundary condition and in the fact that the positive heat source replaces the superadiabatic source QA from formula 4.8. So superadiabatic in our is replaced, and the condition of continuity divergence condition replaces by anelastic condition, which is just the divergence of the momentum rho over V. Everything that I've spoken about, I just remind you, and this approximation is true for the obtainment almost adiabatic system. This previous my approximation, which I wrote down on all these pages. So only when the following conditions are satisfied. This condition is written here, but let me write it down and comment. The condition is like that. Here we start to involve some typical value. We just can write down this condition and the main condition under which the previous system was derived, that the ratio of Cp over adiabatic T in terms of the temperature. And here we have new notation star, I think that it's quite a convenient notation just to mark characteristic value. So what is following after the situation when we have this characteristic value, and so this is the deviation from the adiabatic temperature like this, and so it's also we just mark it by cross. And also there is a contribution of the pressure, but the temperature contribution is much more than contribution from the pressure to the buoyancy. And it's written like this, and it's actually depend on the characteristic value, but not density. It's I should stress that this is the deviation of the density from the adiabatic state. So this deviation is quite tiny, but in terms of the adiabatic state, it could be quite substantial actually to drive all the picture, because actually this deviation of the density actually drive everything. Because when this deviation, for example, when it becomes some place becomes hotter, its density becomes slightly less, and then its place goes up. So actually this works like the main source of the convection. And the previous system which I showed you on the screen at the finish of my previous lecture is based on this assumption. Let's now to prove it. Now we try to prove this assumption. Rosta. Pista, sorry. No, pista, yeah, you're right, yeah. Sorry. Okay, sorry. Thank you for, it's my fault. Yes, of course, pista. So, again, sorry, I spoke wrongly, because when I wrote this, rosta, I start to think that it's about buoyancy, but it's another game. Thank you for correction. I just write wrongly. Sorry. So actually here we set the condition that the variation in the buoyancy due to temperature, typical temperature, is much more than due to the variation of the pressure. So in these old terms, as already I showed you, we neglect corresponding term and keeping only this term, which is responsible for this. So this is the point, and now we show how to prove it, starting from the typical value. For the typical adiabatic value of the temperature and pressure, so which should understand how to get it. And in order to estimate the accuracy of results of the previous section, the feasibility of formula 47b and this new formula 47b 47 and 48, this A and this 48b, we will estimate the typical scale, amplitude, or average from the model. Actually, this is has a different name, this value which is marked by star. So it has many names. And so we estimate this value of the main adiabatic quantities in the Earth's core by the order of magnitude. This is actually the case when of course, there is different way to estimate this characteristic value. And before this work, which was done by me and my co-author, it was some works who estimated also this typical value, but from another point of view. They involve, first of all, the boundary condition. And following the boundary condition, they tried to estimate all this stuff. But on my view, it's maybe not so good way, because actually, if you remember the boundary condition, especially for entropy, they are somehow dependent on the buoyancy layer of the boundary layers, and so everything that it's known to involve the true value term. So unlike the Onufriev and Koppel, Christensen and Albert, we will following actually my work with Chris Jones and proceed from the fact that the typical quantity should be practically independent of the uncertainly determinant transfer coefficient and boundary condition. You know that if you start from the boundary condition, then especially in the entropy case, you should involve sort of some diffusion, some transfer coefficient, which is quite poorly known. And even we can state that this viscosity effect, which is linked with these boundary layers, it's a diffusional effect if you consider the entropy equation. So this play maybe not so main role, especially in the bulk volume of the liquid core. Of course, it plays some role on the boundaries, but now our goal is to get the characteristic value well outside of the boundary in the main body. So this for well-developed convection, the typical convective time T equal, we will consider typical convective time T star, and it's obviously equal to the typical radius. I should stress this is not the radius of the problem, but this is the typical radius which is actually working in derivatives. So if we take the derivatives with some space, not necessarily error in latitudinal in any direction, so there is some characteristic derivatives, and we just obtain this typical scale from these derivatives. This is not connected to the geometry of the problem. It's connected to the, actually, as I will follow in the following, I'll show that it's, actually it's expressed okay. Actually, it's expressed through both the typical size and the typical radial velocity. And from the energy considerations, if you see in the previous section, we equate the rate of change of the kinetic energy to the typical work of buoyant force. Okay, for that we see the okay. For that we see that the if we equate, okay, let's first put on the first place. Here we have the typical scale, and then we have the inertial term, which includes typical density. Then it's include square of the velocity. You remember u grad u, so there is square up here, and everything is divided. If we consider in terms of time, it's divided by t, and we expand this t like that. We divide over t, but t is equal just typical size on velocity, so we can put here again typical size of velocity. So we have this manipulation, and this is also if we multiply by the, actually we have this relation, if we multiply by the velocity the equation of the Navier-Stokes, and the major term is the inertial term, and we estimated it like that. And also there is the Coriolis, there is buoyancy acceleration term, so we just introduce special notation for the acceleration of the buoyancy, also with star. This is acceleration due to the buoyancy, and in our notation, which we adopt in our previous system, this work of the buoyancy force, it was obtained by the just multiplying by v, and then this also there is a main drive, which is actually this entropy value. So it's, let's number this formula 49A. This is the starting formula for the estimation of the typical value. And here, again, I remind you that the index star marks the typical value. For example, let's now just consider some example which is going from the other estimations. For example, this R star is approximately equal it's approximately equal 8 Kelvin, 8 Kelvin per kilogram per mass cubed. Well, not cubed, 4 minus 4 in force power. Okay. Then actually it corresponds to the given Archimedean acceleration. So actually it corresponds this Archimedean acceleration or the if you like buoyancy acceleration, which is equivalent to expansion coefficient, adiabatic temperature, then the density, and this is how we have module of the gravitational potential. Of course, it's about the adiabatic part, and also divided by Cp. So in fact, we can have some very good estimated part for this value. So then, since the Coriolis force does not do work, it is not included in this relation. So we are not with Coriolis force because it does not create any work, and this is actually related to the work of the stuff. So dominating the equation of motion for 4R, it balances with the gradient of superadiabatic pressure, and we estimate the force balance by taking the, actually to make this estimation, we should estimate the force balance by taking the rotor or hull from 4.4a equation, which is actually Navier-Stokes equation, and getting rid of the pressure. So after that we have the following two estimation, one which is connected with pressure and another with Coriolis force regarding the pressure, and with Coriolis force which regard again this buoyancy term. So we have the estimation Coriolis force itself. Of course, more precisely to say, this is not Coriolis force, this is Coriolis acceleration. So it's, from one point of view, it's equal P star over outer core. Because here when we take the derivatives, it's only in that direction, and it's just slightly changed in that direction, as already told. So we have here this P, Rho, and now density. And then another relation we have, which is related to the buoyancy term, rho omega V star over outer core radius, and then it's everything balanced by the buoyancy acceleration, which well known as well already told to you. Divided by typical size R star. Okay, this is equation 4.9 BC. So here the radius of the outer core RO, which is much more than R star. It's necessary to know that RO is much more than R star, just because this is the real radius of the problem, and this is value radius which appear in the derivatives to the different values. So in accordance with the Taylor-Proudman theorem, which was commented regarding to this flow by Braginsky and Roberts and Busse in 95 and 2002. And so we complete system 4.9 by the estimation which was done by myself and Chris Jones in 2002. So 20 with something less ago. The balance on convective heat transfer and superadiabatic heating from the integral of the general heat transfer equation 4.78, which is of course related to the entropy. This balance can be written by rather simple formula. Typical rho, typical temperature, capital temperature mean adiabatic temperature, of course. And then here we have typical velocity divided by RO, and then we have typical entropy. And this is the final formula for 9D. Okay, actually we have three equations and three unknown. What is the unknown we are looking for? The unknown is velocity. Then we have all this rest is unknown is velocity, which we want to find. Also unknown is the radius which we have, and another unknown is the deviation of the entropy S star. So for all these three unknown, after all this manipulation, which also listed here on this table, we are resulting in the following relations. So we just involve all the stuff, and eventually we get some. Maybe there is maybe not so correct representation, because some values with star are exactly known. For example, this rho, temperature, and some values that we just estimated, this typical velocity, entropy, and radius. Actually, we estimated only three values. And the rest of the value, including that which we add with the star, are rather well known. So we just take them from the independent researchers. So let us determine for the obtained system, which consists from A49, A, B, C, D. Actually, in this system we also have pressure. So actually there are four unknown and four equations. These four equations are all numbered with 4.9. So from A, B, C, and D. So actually there is four equations and four unknown. Let me stress again that unknown is deviation of the pressure, deviation of the entropy, and velocity itself, of course, unknown. And another quite important parameter is the typical scale. This one, which is much less than the scale of the problem, initial scale of the problem. Okay, let's determine from the obtained system typical superadiabatic quantities. I will I don't know, is it enough? Okay, I'll try to fit in below as a result. So for V star, we obtain square root of the fifth power of RO in cube. Then we have this typical flow in squared. Then we have Archimedean acceleration or buoyancy acceleration in squared. Then there is density in fourth power, temperature, adiabatic of course temperature, also typical in second power, and there is omega. Okay, and if we put the known for the Earth value, then we have the estimate to about 2 millimeters per second. Then we can estimate typical R. Of course, we have the similar expression. Okay, maybe. Oh, maybe I missed one equation. So one A for 9B C for 9D. Ah, it's here. Oh, I didn't write it completely. Sorry. I didn't write it completely. I didn't write it in full. Sorry. Thank you again for my mistake. So this value is equal to just this heat flux, which is well known. This is adiabatic heat flux, and it's equal to this equation. So there is some small addition here. 49D. Sorry, I missed this term. So now it's co-appear here as well, and it's quite well known, it's just adiabatic heat flux. Then for radius, we have the similar expression again in fifth root. Squared cube and okay, and then this is two formula 4.10 A and B. And the remaining term, this is two term, which is quite realistic. This one of order 2 millimeters per second is rather well known, and it corresponds to the movement of some peculiarities in magnetic field. When around some thousand years, the complete circle of all this magnetic variation is occur, and you can see it on the geomagnetic variation. And here also there is some size, which is, if we put some typical for the Earth stuff, then it will be equal about, okay, let's put it this way, about 1/10 of the thickness of the outer core. Oh no, inner core. Oh, outer or 1/20 of the thickness. So it's indeed we satisfy this condition which we wrote previously, because this RO is of order 3.5 to the 10 to the 6th power. So it's 30 times more larger. This value which related to derivatives in comparison with the real geometrical value. And much more simple formula appears for the entropy deviation. Let's put it here. It's just R by rho without any root. Omega. And now, of course, we're using the trick to remove this complexity. We just repeat this value here to make the relation more simple.